All right, welcome back, everybody. Hopefully, this finds you healthy, happy, and coronavirus free. Um, by now, maybe you and your family are starting to get on each other's nerves due to social distancing and everybody being at home, stuck in a house together. Hey, guess what? This is a great time to say, I got to go study and lock yourself in your bedroom away from everybody. Okay? Great excuse. Nothing like parents want to hear more than, I've got to go study. Makes them happy, makes you happy, everybody's happy. Okay? Today we're going to go over chapter 19. This is a two-part, okay, series because the slides were about 30. And I know the last couple seemed really long and kind of drawn out and a little rushed. And that was because the slides, there was only like 29 slides or 28 slides. And I wanted to get it all done in one rather than having a 10-minute video here and a 10-minute video there. I decided, you know what, let's go ahead, and then they ended up a little long. Well, this one's got over 30 slides, so I said, you know what, let's break this in half. We're going to do 15 or 16 and then 15 or 16, okay? So this is a two-part. So this is part one, okay? Chapter 19, Glacial Modification of Terrain. If there's one thing I love other than volcanoes, glaciers. Man, they're cool. I would love to live during an ice age. Now, I say that. I'm an old man, I can say that, okay? Anyway, again, we're going to use the McKnight's Physical Geography, a Landscape Appreciation, published by Pearson, 12th edition, okay? All right, so let's get rolling here. All right, so these are some of the topics we're going to go over. Again, this is a two-part series, so we'll get through about half of them. Types of glaciers, glaciations, past and present glacier formation movement, the effects of glaciers, continental ice sheets. Wait till you see the one that was over North America. Mountain glaciers. Oh, that's cool too. And the paraglacial environment and causes of Pleistocene glaciations. Whoa, hey, that's my favorite topic. That has to do with me. That's right down my research area, right? The demise of the mammoth, okay? Pleistocene glaciations. Why did the mammoths die out? Did they die out from humans? Environmental? What was it, okay? So anyway, causes of Pleistocene glaciation. All right, types of glaciers. Snowpack over years turns to ice. Remember, snow builds up, and it's just kind of like faulting and folding or sedimentary rocks. Okay, you're putting more pressure, more weight, more pressure, and they begin to cement together basically and start compacting. As it's compacting, it's squeezing out all that excess air that's in the snow and everything else and turning it into ice. Okay? Ice mass, motion under gravity grinds everything in its path, okay? This is the #1 sculptor behind water, okay? Behind water, #1 sculptor of the landscape. The thing is, water, yeah, if you got enough of it, it can do a lot of damage, like floods and hurricanes and stuff, granted. But rivers and stuff, they sculpt slowly, okay? But the thing is, we have a lot of rivers, so there's a lot of sculpting going on. Glaciers, on the other hand, especially ice sheets and glaciers, whenever we were back during the Pleistocene, they did some major resculpting and sculpting of the landscape and damage, okay? They tore some stuff up because glaciers are huge and they pick up these big boulders. We're not talking sand, silt, and clay like a river. We're talking big house-size boulders, okay? And they're moving them around. They're pulverizing, grinding, and beating them down into sand, silt, and clay. So imagine taking a whole mountain and just crumbling it under the weight of the ice, okay? Glaciation increases the erosion rate on a mountain by at least 10 times that of unglaciated mountains. So in other words, water can increase erosion, right? But glaciation, 10 times that of water, okay? It can also modify flat landscapes as well, depending on how far out it extends. You may think, oh, well, it's extending out and that's where the damage is done. No, it's actually all the meltwater and the lust and everything else that is moving away from the glacier, okay? It all gets washed out. When it gets washed out, it goes out onto the flat plains and stuff, okay? All right, continental ice sheets exist in non-mountainous areas. Non-mountainous. If it's mountainous, it's an ice field, all right? Here, let me turn my little pin on here. Boom, there's my little pin. Boom. Ice field, that's in mountainous area. Non-mountainous areas, okay, you're talking Antarctica and Greenland. We only have 2 ice sheets now. We used to have more than that, but right now we're down to 2. So that tells you how much global, the Earth has warmed up in the last, 12,000 years or so, okay? Say the last 23, actually. So we've had some cold spikes in between. But anyway, about 23,000 years ago was when we were at what we call the glacial maximum, Okay, the glacial maximum. That's when the ice was at its fullest extent, and then everything started melting from there. Okay. Mountain glacier, highland ice fields. There, that's ice field again. So in mountainous areas, okay, we have ice fields, right? Ice sheets that submerge most underlying topography, so you don't see them, all right? If you look at some photos of Antarctica, which I think we looked at in class, the peaks are just now starting to come out of these ice fields, okay? And everybody at first thought, oh, pyramids, aliens. Well, don't get me wrong, I still believe in aliens, but hey, that's crazy me, right? But no, these were the tops. These are the peaks of the mountains. So imagine, how tall are those mountains? Are they 15,000 feet, 20,000 feet, 30,000? How tall are they? We really don't know. The ice isn't gone yet. So the mountain peaks are just starting to be exposed, right? The valley and, of course, the Piedmont glaciers, those that are coming down off of the mountains. All right, alpine glaciers develop individually instead of part of an ice field. We call these cirque glaciers. And we're going to get into a picture here in a minute. We have cirque glaciers here, but this really isn't a very good picture. We'll see it here in a minute. What's the takeaway from this slide? Well, a little pinnacle of a peak that's poking through an ice field is known as a nunatak. You need to probably remember that. I think you just might see that again, right? And, of course, here's our valley glacier, okay? Ooh, right there, okay? Extending out of the mountains. All right, glacial ice volume has varied considerably over the last few million years. Right? Again, we are at our lowest extent right now. Mount Kilimanjaro in Africa, believe it or not, has glaciers on it. But these are cirque glaciers, it's a mountain, but they're shrinking. Even the ones in Montana, all right, that we have here in the United States, okay, Glacier Monument National Park, they're moving, they're retreating, and they're disappearing at an alarming rate, okay? We're not going to have them for long. So if you want to go somewhere and see something really cool and say, hey, I climbed a glacier without dying, like on people on Mount Everest, which we'll get into here in a minute, go to someplace like Glacial Monument, right? Everybody can kind of hike up and look at it, and you can say, hey, at least I was on a mountain where a glacier was. But you better do it quick, because those things are disappearing. They're going bye-bye. See you later, right? The evidence left behind allows scientists to determine the chronology of past glaciations. We're going to get into that. That's debatable, right? We do get some information, but we can't get all the information. And I'll explain that when we get to moraines and terminal moraines, because glaciers actually destroy evidence of their past, okay? They leave some of it behind, but a vast amount of evidence gets destroyed by the glacier itself. So we're going to get into that later. Pleistocene glaciation. So it began at least 2.59 million years ago, right? That's when the Pleistocene began. That's when we kind of went into this whole glaciation of about every 100,000 years or so, okay? The last major ice retreat only occurred 9,000 years ago, okay? Right there at, I wouldn't say it's the beginning of the Holocene. Holocene started around the 12,000, but 9,000, that's when we really started seeing glaciation start melting. Now, again, the glacial maximum was right around 23,000. So we had some slow melt off, and then as the earth warmed up and more ground, remember, go back to our things here, more ground you have, the more heat it absorbs, right, because it's dark. The more ice it melts, the bigger the ground becomes, the larger the area, absorbs more heat, melts more ice, so on and so on. We've talked about that before in class, right? All right, okay, so here we go. It started melting around 23,000 years ago, and then enough ground was exposed to absorb enough heat and build enough temperature that then around 9,000 years ago, it started really going, all right? And that was the beginning of some major deglaciation, okay? Dominant environmental characteristics was refrigeration of high latitude and high elevation areas. Remember, elevation correlates to latitude. There's a difference, though. You got to go whatever 1,500, 2,000 miles in latitude to get to tundra and ice and what have you. On a mountain, you only got to go up about, it depends if it's winter or not, 14,000, 15,000 feet. Okay? Consistent alterations of glacial and interglacial periods. So we have had for the last 2.59 million years these ups and downs, peaks and valleys, right? So it's warm, it gets cold. It gets warm, it gets cold. So anyway, these have went up and down for the last 2.59 million years, okay? The Wisconsin, the last one, they used to give names to them. Now they call them, MIS and different things. So we had MIS, this, and this. But anyway, I'm not going to get into too much of that. If you want to take a course, we'll discuss that later. But they used to give them names, and this last glacial maximum was called the Wisconsin Glacial Stage. It marked the end of glaciation. Okay. Now, a lot of people tell you it's in. Actually, they say we're still in a glaciation right now. That you're not really out until you've totally peaked at the heat, and then begin the cool-off period. Okay. So you're still in a glaciation because you haven't hit that peak in heat yet and total deglaciation. Once you hit it, that's when you're considered in an interglacial until you hit the cold peak again on the other side. Okay, so cold peak here, go up. I'm still glaciated. I'm still in a glacial time period. I hit the peak, and then it becomes interglacial as it goes back down to where you hit the cold spot again. Okay, so anyway, at peak. So 1/3 of total land covered in ice. Man, imagine if there's that much ice. How you take all the people we have today and take away all that land, right? No, where are people going to live? You can't live on ain't nothing living on a glacier, right? Nothing's living on Antarctica, right? Everything dies, okay? So you got to now take all those people and you got to cram them into a smaller area. Ooh, something tells me that is not a good recipe for health, okay? Or long life. All right, so Pleistocene glaciation, the Laurentide ice and the driftless areas, okay? So the Laurentide ice sheet, that's the big one. You're going to see it on the next slide. It went all the way from the Colorado Rockies to Greenland, all the way from the Arctic down to about Nebraska, okay? So, I mean, that's a huge expanse of ice, okay? Huge area of ice, all right? All right, so some indirect effects of Pleistocene glaciation, periglacial processes, all right? Periglacial zone where ice never existed, but glacial factors affected the landscape, such as erosion from the ice melt and solifluction, otherwise permafrost and stuff. It's so cold, the glacier and the ice ain't touching it, but you got to remember, even though it's there, it's still having an effect on everything around it, right? So everything around it is frozen as well because the glacier is so cold, all right? So that's periglacial, right? It's not actually touched by the ice, but it's been drastically altered by the ice, okay? Meltwater, that's a big one, right? Everything it melts on the bottom is coming out flooding, so you get the boulders and you get the rocks and sand and all that other stuff. The lust deposits, that windblown silt, some people call it glacial flour and what have you, coming off there. It's a fine powder, right? It gets blown and deposited in places. Those are periglacial. Never actually touched by the glacier, but they're part of the glacier, okay? They were affected by the glacier, right? Sea level changes, buildup of ice continents led to less drained water in the continents and brought about lowering of sea levels. Now, we've talked about this in class. This is isostasy again, right? So, again, I'm going to try and do this. Hopefully you can see me. Isostasy, when you have ice in the middle of the continent, it causes the edges to bow up, right? Which means if the edges of the continent bow up, sea level goes down. So that's one thing that affects overall sea level. Now, because you have all that ice, there is also less water. So the continents are bowed up, causing sea level to go down, and there's less overall water causing sea level to go down. Now, when the continental ice melts, the edges drop back, water drains back, the water from the ice has melted and now returned to the ocean. So the edge of the continent drops down, sea level rises, as well as adding extra water to the oceans and the seas, right? So isostasy, there's two different things there. Isostatic rebound, remember that, okay? Crustal depression, that's what we're talking about right now. The weight of the ice on the continents caused continents to sink. Ice melted allowed for continents to rebound. We just talked about that. Pluvial developments. Okay, so alluvial, fluvial, alluvium, fluvial, rivers and streams. Pluvial, ice. Aeolian, windblown. Okay, so those are the three main words that are topics that we've been talking about lately. All right, Aeolian, windblown, fluvial, water, and pluvial, ice. There you go. Simple as that. Pluvial developments, considerable runoff, and I can't see that because it covered my face. Anyway, moisture leading to increased precipitation and what have you, and develop many lakes, including the Great Salt Lakes and Lake Bonneville. Remember, most of the lakes, natural lakes, are a direct and are directly associated with glaciation, whether it's the meltwater runoff, the Great Lakes. The Laurentide ice sheet had Lake Agassiz. It was as big as all the Great Lakes put together, but it was on the ice. And parts of the ice would break out, and these huge pulse water flushes would come down all the way, flooding out the Mississippi River Valley and going all the way into the Gulf. They've studied these. They've got soil samples and strata samples from the Gulf of Mexico, and it shows all this material from these pulse water rushes coming off the Laurentide ice sheet. And then the chunks of little icebergs that are in this huge lake would block up the hole for a while. It'd refreeze, reform, and then some melting would go on, and then it'd break through, and you'd have a pulse water flush again. Okay, so they've got records of these. All right. All right, here we go. This shows you just how big the Laurentide ice sheet was. Okay, here's my little pen. And my little pen isn't going to work right now. Don't know why, but this computer has been acting up a little bit lately. There we go. There's my pen. Look at the Laurentide ice sheet all the way around to Greenland, right? And a second one, look at this, all the way here. Now, here's that Bering Land Bridge, right? Boom, all the way from Siberia, right? That's how they say the mammoths and stuff got back and forth. Again, we used to have camels and horses and everything else here, right? Rhinoceros, flat-nosed bear, direwolves, saber-tooths, and they all used to migrate back and forth, okay, across the Bering Land Bridge. Now, they could only migrate if there was a food source for them. So mammoths migrated frequently back and forth, but some of them just went extinct because there was no food supply for them to travel and stay in. Some of them, it was temperature. Mammoths and them could handle the temperature. Some of them, the animals couldn't. Okay, we had 31 species just here in North America. 31 species of what we call megafaunal species go extinct at the end of the last glacial maximum. So by the time the Laurentide ice sheet melted, around 23,000, well, 23,000, but somewhere in that time frame. By the time all the ice melted from that time frame, 31 what we call megafauna species, saber-toothed mammoths, everything, went extinct in North America. So there was something going on there. A lot of people blame it on the environmental change, that they had gotten used to the ice age. They had gotten used to the areas where there was water, wasn't water, and then things started warming up, and they just couldn't handle the back and forth, the constantly up and down, cool, dry, wet, warm. The environmentals, they just couldn't handle it. So anyway, that's one of the hypotheses. The other one is that man came over here at around the same time, 12,000 years ago, came across the Bering Land Bridge and hunted them all into extinction. Okay, that's hard to believe. I think it was a combination of the two. I think they were already on the demise from environmental things, and then man came in and finished them off. Okay. All right, so contemporary glaciation. So you look where we were, and now you see where we are. Okay, here is Greenland, and here is Antarctica. That's all that's got ice now. Some of the mountains do, but that's really all that's got ice. Limited ice cover today, about 10%. So instead of 1/3, it's down to 10%. Okay, of total land surface. 96% of total ice cover is in Greenland and Antarctica. And here's those mountain peaks I'm talking about, right? They're just now starting to pop up, right? Okay, out here in Antarctica, and a lot of people are like, "Oh, pyramids." Trust me, I'm looking for a pyramid too, but I can tell that's a nice mountaintop right there. But imagine how big are these mountains? So that goes to tell you how many feet of ice. Is there 15,000 foot of ice there? How much ice? There's a lot of ice there. Okay. Antarctic ice cap consists of two unequal sections, and we're going to get in that when we see the Antarctic ice cap here in a minute, when we're talking about climate change. Unequal separated by the trans-Antarctic mountains. Okay, there you go. See the figure. So West Antarctica has a few dry valleys. There's actually places that are so low that ice and stuff doesn't get into them. There's no moisture, nothing down there. It's just dry. Okay. And then we got the Greenland ice cap. The Greenland ice cap is really starting to melt off. Well, Antarctica is too. I've told you in class, right? There are chunks like, not too long ago, one the size of Delaware broke off. And it goes to, is that fresh water going to mess with the conveyor belt, the thermal halide, circulation? What's going on here? Because we add and change the complexities of the ocean, we could kill out all of our food supply, right? So we got to be careful. All right. The Greenland ice cap, though, it's melting, and it's melting rapidly, right? It's unprecedented how fast it's melting. And they're starting to find archaeological sites there that people were actually there at one time. And the ice is starting to melt and uncover a lot of these archaeological sites where, oh, wait a minute, somebody was here. There was fields here and walls here, and what's going on? So we know at one time people lived there, okay? North American glaciers, again, if you want to see a glacier, you got to go like Glacier Monument National Park, someplace like that. That's the only place you're going to find them because they're pretty much extinct when it comes to North America. Now, it doesn't mean that they can't come back. They can always come back. We hit another ice age anytime. Like I said, Mother Nature likes to correct issues when there's something that's happening. And right now, she may be thinking, I'm tired of all these people, right? All right, and here's our Transantarctic Mountains right here. Boom, boom, boom. All right, here's the major part of the ice sheet. Okay, this is the major right here. Okay, this is all ice shelf. That's ice extending off of, okay, we're just going to do that right there, off of the actual land. So it's extended out over water, and the warmer that water gets, the more it eats and erodes away underneath, causing those big chunks to drop off. This, believe it or not, okay, over here where they're showing this warm area right here, believe it or not, these are islands, okay? Most of this here is islands, okay? There's a little island right there. So this is all ice shelf for the most part, okay? So imagine that big chunk right there breaking off, falling in the ocean. Talking about cooling things off quickly, changing salinity, changing pH, it will slow that thermal haline circulation down to almost nothing. And then what happens? Well, if you're not moving the warm water from the equator to the northern latitudes, it keeps everything circulating, that convection cell going. If the convection cell ain't going, that means cold gets colder, warm gets warmer. Okay? So you start packing too much heat at the equator and no heat at the poles. Okay? And then again, high flow rates of outlet glaciers. These outlet glaciers, again, glacier wash, it's moving all that pulse water into the oceans, okay? So we got that going on too. All right, so glacier formation and movement requires a balance between accumulation and ablation. Otherwise, how much you're making to how much you're losing. Accumulation, building, ablation, taking away, okay? Snow begins as crystallized water vapor. Remember what I told you? It always looks like it's snowing at the poles, right? You always see it's like, oh, it's snowing all the time. No, it is a dry ice desert. Okay, remember that. What you are seeing, all them little flakes falling, that's the water vapor. Okay, that's what's the water vapor in the air literally freezing out, which is why you got to cover your mouth with something, keep that warmth in, because if you just take your stuff off and you're like, you're putting all that cold air into your lungs, and your lungs have water vapor in them. So now you're freezing your lungs, and you end up with lung conditions, okay? So make sure when you go, remember, you can always become more dehydrated quicker, easier in cold places, all right? And at the same time, you can freeze your lungs and everything else. So make sure you protect yourself. Drink lots of water, cover yourself, keep the heat in, keep the cold out, okay? Compressed to a granular form. Again, as that ice begins to build up, it presses, and begins to build in depth. Right, so there we got our snowflakes, right? Here's our snowflakes. Again, you can see how much airspace there is between flakes and water and everything. And as it builds up, it turns into granular snow. And then it starts getting compacted, right? And it becomes glacial ice right there, all right? Again, more compression causes the granules, I cannot talk, to coalesce. You need to know these words. The coalescing or the granules coalescing into ice is known as nave or firn. You need to know that. You might see it again. And then further compression results in glacial ice, okay? Your ablation and accumulation zones. We're going to see those on the next slide or so. So we're going to take and go ahead and flip over there now. Oh, what is this? This is an in-class prompt. All right. So I've traveled a little bit in my life, nothing recently, back when I was a much younger man with the military. And I got to travel around and see some fantastic and wonderful things. One of the wonderful places I got to go and spend 3 years of my life at was Japan. And I got to travel around and see quite a bit of Japan. I was stationed in Okinawa, Japan, scuba diving, all kinds of good stuff. It was awesome, right? And you're going to see more about that in chapter 20, okay? So anyway, here we go. One of the places I had to go on a military exercise was a joint military operation with the Japanese on the island of Hokkaido. It is the furthest northern island in the chain of islands. It is like 12 miles off of Siberia, off Russia. In fact, we got buzzed by a couple of MiGs every once in a while. They'd come flying over, and all of a sudden, woo, the alarms would go off, the sirens would go off, and we'd run outside, and a couple of MiGs would drop down low and go, right? That was awesome. Now, Okinawa is where most of the military bases are, but the Okinawans don't really like America all that much. Not the majority of them. In fact, where I was stationed was actually the communist district, and trust me, I was in Yamitan Village. What's Yamitan Village? Have you seen The Karate Kid? Guess what? That's fake, okay? I was in Yamitan Village. Doesn't look nothing like the movie. I flew into Kadena Air Base. Doesn't look like nothing like the movie, okay? That's totally made, movie's totally made up, okay? I was in Yamitan Village. And it was the most, what I call it, communist area. So when special forces and all of them would jump and stuff, they get out in their cars and try to actually run people over. They try to run you over in the streets, whatever. So anyway, it was all good. And then you get to Japan. And depending on where you're at in Japan, they really either like you and accept you, and they're like, hey, come on in, let's party, have a good time. Or you get the crossed arms and they tell you to get out because they still remember Nagasaki and Hiroshima. Still not happy in some places, okay? So it all depends on who you run into. But then you get to Hokkaido. Hokkaido's a whole different monster, okay? Hokkaido totally embraced Western and European architecture. So I get there, I'm astounded. Like their city hall, the Sapporo City Hall, was an exact replica of Ben Franklin's house, okay? And they had cabins and this, that, and the other, and these old buildings, and it was an awesome place, one of the most spectacular places I ever went. But they're covered in snow and ice for most of the year, okay? So anyway, again, right off Siberia, so it stays cold there. So anyway, it looks like something like you're stepping out of the Old West or Old World, right? The Sapporo beer factory there, Sapporo beer, was an exact replica of a German beer factory, okay? An exact replica. And so it's literally like stepping back in time, right? And it's like, wow, this is cool, right? But there's going to be some other things, and you'll see it here in a minute. So anyway, one of the things they have there is the Hokkaido or Sapporo Snow Festival, okay? And they bring in these big chunks of ice. And now they've got this big, huge flat area. I mean, I can't tell you how many football fields it is. It's a huge, just humongous flat area. And in the wintertime, they fly in all these big ice chunks or bring them in by truck, however, and then they start putting them together and sculpting them, right? And these are literally life-size sculptures, all right? So here we got one of a temple right here, right? That's a temple, okay? It's life-size, okay? You can see the regular building back here, right there. That's a regular building. Look at that. What is it? 1, 2, 3, 4, 5, 6 or 7 stories tall. Okay, and this thing, yes, granted the picture's at an angle, but it just gives you an idea of still how big this is. All right, here's some dinosaurs here. Look at this. These are the tourists. Those are the people. Okay, so it gives you these things are on a grand scale. So if you get a chance, look up the Sapporo Snow Festival or Hokkaido Ice Festival, whichever one you want to call it. Look those up. Look at some of those pictures. It's even more spectacular at night. It's cool. I got to be there for it. It was awesome. Okay. Oh, wait a minute. A second in-class prompt. 2 in a row for this chapter. Man, and you know what I was thinking when I was putting this chapter together? I was like, man, what am I going to put on this chapter? It's like, what have I ever been to? And I went, oh, Hokkaido. I told you it was a cool place. So it's old world up on top, but guess what? Underneath, it's new world. Okay, they have the world's largest underground mall. All right, literally, this here is like a street sign. Okay, it tells you where you're at and what's above you. Okay, tells you where you're at. Well, it stays cold there. People don't like to drive. You know, they don't want to run around all bundled up. Look at this. They're wearing dresses and skirts, no coats. That's because they take the subway to their apartments and stuff and different things. It's all underground. And even this, you see the skylight here, right? It's all underground, okay? This is all underground. So it's really cool. So it's old world on top meets new world underneath. And under this part here, the above part is where the ice festival was. So you see this huge, like such enormous, like as big as an airport, right? With all the landing zones. You're like, why is all this unused land out here? And you see what they do for the ice festival. It's like, well, what do they do for the rest of the year? Well, guess what? Underneath is a world all of its own. So anyway, Hokkaido, Japan, world's largest underground shopping mall. Cool. All right, now we're back to our glacier formation movement. So we took a quick break, went and did that, now we're back. So glacial flow is orderly sliding of the ice molecules are sliding along, right? Ice under extreme pressure deforms instead of slipping, right? So it can deform, moves around, different things. All right, here we go. Meltwater contributes to surface for glaciation to slide on. Basal slip. It's the meltwater underneath that's allowing that stuff to move. So we have plastic flow, which is the ice moving, and then you have the basal slip, which is the meltwater helping it move. So there's two different movements. The glacier can move on its own because it's growing, or it can move because there's meltwater underneath and it's sliding on that meltwater, okay? So here is our accumulation zone. What does that mean? The accumulation there, okay, is where you make more ice than you lose. Ablation is loss, accumulation is gain. So I gain more ice than I'm losing. The opposite is for the ablation zone. The ablation zone is where I'm losing more ice than I'm gaining. So you have this ebb and flow depending on how cold or warm it is, all right? And your equilibrium line is what separates the two, okay? That equilibrium line, it kind of stays, pretty much where it's at. It's either growing or shrinking, okay? Glacial flow versus glacial advance, again, comes back kind of to, is the glacier moving because it's growing, right? Or is it advancing, or I should say advancing because it's growing, or is it flowing because it's moving because of basal slip, okay? So there's a little bit. Now, I'm not a glacier person by any means. I think they're cool. But if you want to look up more on the topic, that's cool too. Check out your book. It's all good, okay? All right, so glacial retreat. So glaciers do retreat. Now, I got to remember, glaciers do a lot of changing the landscape. I don't want to say destroying it, they just change it, right? So here we go, we're glacial retreat, okay? This is either a lobe or a glacier or whatever you want to call it, but you can see it does this right here. So here's a rock, it picks a rock up, it moves the rock to the top, and then as it retreats, it's going to drop that rock out. That's called plucking, okay? Glacier plucking, right? Now, that rock is as big as a house, okay? That's not no little rock, that's a big rock. Okay, because all the light stuff, it's so windy on the glacier and dry that all the light stuff flies away, okay? So here we go, my glacier is advanced, and then it begins to retreat. And as it begins to retreat, it starts dropping out some of this debris, all right? And that's called glacial till, right? Glacial till. We'll get into that, you'll see here in a minute. All right, erosion by glaciers. All right, look how smooth this is, right? It's smooth. Why, that rock was just forced along and it tore up everything in its path, right? Volume and speed determine the success of glacial erosion. How cold is it? Is the glacier growing? Is it moving? Now, I should have said this on the last one, the accumulation ablation zone. For a glacier to move, it needs about 50 meters of ice. That's a thick chunk of ice, okay? So to get it moving under its own weight, because that's what it is, it gets weight, it starts pushing down and moving. To get it under its own weight, you got to have about 50 meters. So imagine that much ice. So you got that much weight with a big old house-sized boulder, and you are just tearing some stuff up, okay? Erosive power of moving ice slightly larger than that of water. So again, it's more destructive than water. There's just less glaciers, but more destructive, okay? Glacial plucking, we already talked about that. Picking up a rock material through refreezing of the meltwater. So you got that meltwater on the bottom, it gets refrozen in, but it always moves to the top. Now, you got the end where that till is. Believe it or not, when you get up towards those equilibrium line in the ablation zone, there's no debris in there, okay? All that material, the till and everything, is all at the far end of that lobe, down at what we call the terminal moraine. And we'll see that again here in a minute, but that's where all that material's at. The majority of that ice, they say glacier water, ice sheet water, that blue ice, they say that's some of the most purest, best water in the world. And it doesn't have dirt or nothing in it. That all happens, all that dirt and debris and everything happens on the outside edges, not the center, okay? Glacial abrasion, bedrock worn down by rock debris and embedded in the glacier. Again, just scouring it down. And then we have the subglacial meltwater and erosion. So you got things going on below too, because you put all that ice on top of the ground. We still have a molten core in the earth, so you still got some heat coming up, right? And so the ground is still a little warm underneath. Don't get me wrong, it's frozen, but it's still got some warmth in it compared to the glacier. So you always end up with that slick film of meltwater, which causes that basal slip, okay? And so you always end up with that film because you put that ice on there, it's like insulation, like people living in an igloo, right? All you're doing is getting rid of the wind and stuff, right? You get inside, you can stay warm because you're staying out of the wind and everything else, right? And your body heat will eventually start to fill up that igloo space, okay? All right, transportation of glaciers. Again, look at my meltwater river here. That just goes to show you how much water is coming off this glacier. Now imagine how much water is coming off Antarctica, okay? That's a lot of water, okay? Glaciers effective in moving large rock pieces. Again, plucking. You've seen that 2 or 3 times now. What's that telling you? Typically move glacial flour. Okay, that's it. Excuse me. That's that fine, powdery, silty stuff, or lust. Okay, it builds up its glacial flour. It's really fine particles, right? Most rock material transported along the base of the ice. So again, the top, that's fresh water. Okay, it's the bottom. The remaining glacial ice free of rock debris. See that? Free of rock debris, just like I said. Roll of water, flowing water on moving ice and their melt stream. So this is the melt stream here. Again, a lot of water coming out from underneath because that glacier is melting along the bottom and maybe some on the outside, but most of it's coming around the bottom because that ground is heating up. You're exposing the ground. It's taking in the sunlight and the warmth, which is causing more of the ground to heat up. So short wave radiation versus long wave radiation. Remember that? We've talked about that in another chapter. Moulaines, cracks in the ice in which streams run. So this is underneath. These are the cracks in the ice. The cracks at the top of the ice, those are called crevices, okay? And we'll see more about that maybe later. But the crevices, if you've ever watched movies of people going up to like Mount Everest and stuff, they're laying down extension ladders across these things. These are huge, huge ice caverns or ice gorges, whatever you want to call them. They're huge, they're deep. You fall, you're gone, you're never seen again, right? And especially because that ice is moving, right? You fall in, guess what? They will never find your body because now you're part of that glacier moving back and forth, getting ground and pulverized. Okay, so ice in which streams run are the moulaines. These are at the bottom. You can look this up. Some are really cool because the moulaines actually come out of like a little ice cave. Okay, so it's kind of cool. All right, deposition by glaciers. Glaciers move lithospheric material, lithospheric rock, not soil rock. They put off though the loss and stuff from one region to another in vastly different form. Material moved by glaciers is known as drift. All right, material moved by glaciers is known as drift. Till, the rock debris. So the material moved is known as drift. The till is what's left behind. Okay, deposited by moving or melting ice. And then we have these large boulders that are different from surrounding local bedrock, known as glacial erratics. Remember all these. When I went to Yellowstone, they had a big rock like that sitting right in the middle of the forest. In one of the campgrounds, and it had a big sign on it that said left here by the last ice age. So what happened, it had picked this huge big house-sized rock up somewhere and dropped it, and since then, since it was dropped there, trees have grown up around it and everything else. And the trees are kind of at an angle because they kind of got rooted under, so they're kind of like bent up over the rock. But again, still cool. All right, deposition by meltwater. Large portion of debris carried by glacier deposit or redeposited by the meltwater. Those meltwater streams coming out of below it, right? So these subglacial streams from glaciers carry sediment and material. They're just like a regular river, right? And you've seen the one that was flowing in that previous picture, right? So imagine how much material. And again, it depends. Glaciers associated with mountains means you got that gradient. So you got gradient, you got discharge rate, and you've got all this ice and water. So guess what? You have the ability to move a lot of material really fast and pile it up, right? So glacial fluvial, glacier, river. Glacial, fluvial, stream, pluvial. Okay, pluvial associated with glaciers. It's all kind of the same, but you get the idea. Now, I want you to look at this. This here is the sediment left behind. Look at that. Now, this is a regular road here. Look at the distance across that road. That's a 4-lane highway. Look at how high. That's the sediment coming off. So now, don't get me wrong, depends. What's the parent material that this glacier is on? Is it soft material? Is it more resistant material? Okay. How big is the glacier? It's got to be at least 50 meters to be doing some movement, right? So all these factors play a part into the sediment. Now, I don't know, for example, if this was a terminal moraine or if it maybe was a till field, but you got all that sediment put up there, okay? And it could be too, I'm not going to face all of it, but I'm pretty sure that when they made the road, they probably scooped a little bit up there, right? But it just goes to show you how much sediment's in this area and how much damage and reconstructing and moving around that a glacier can do. It can really do a lot of work, okay? All right, that's the end of this chapter, or not the end of this chapter, the end of this part 1. Part 2 will be back right here in a moment, so don't go anywhere. I'll see you in a few moments. Bye.